I'm going to stand next to Phil so I can use the mic. So welcome everyone to the very last MICD seminar of the year. And it's going to be probably the most exciting one. So we have Professor Phil Rowe here. He's certainly not a known commodity to pretty much everyone who does computational fluid dynamics of some sort. But for formality, I'll still go through his bio. So Phil completed his education at Cambridge University and worked for the Royal Aircraft Establishment from 1962 to 1984. And at that time, I do not think you were doing CFD, were you?
No.
Not at all. All right. And so he was working in missile aerodynamics. I remember a very beautiful monograph on hypersonic flows back from that time, right? And then sometime between 1984 and 1990, he worked on numerical methods for compressible flows. And at that time, he devised probably the most well-known numerical method for compressible flows, which is called the Rho solver. And well, he published that paper in the early 80s. I stand corrected. So in 84, he left the Royal Aircraft Establishment and joined Cranfield University. And in 1990, he was attracted to the University of Michigan, probably by Professor Bram van Leer and Ken Powell and a few others here. And they ran an amazing laboratory. It was called, at some point, it was called the Keck Foundation Laboratory for Computational Fluid Dynamics. And as a student growing up in India and learning the ropes of CFD, that seemed to be like a dream factory for me, right? That's the place I wanted to be. And the work that was produced has been inspirational. In any case, he has been in the department since 1990. And as of the last couple of years, he changed his status to Emeritus Professor, but he's no less excited about research and he's been creating new ideas. Just last week, earlier this week, he had a graduate student defend his PhD thesis. He has active collaborations in the US and in Europe. And I am to understand that sometime next year, he's going to Cambridge University to give a lecture or a talk. And we get to have a preview of that today, right? With that introduction, I leave it to Phil. So I will be your eye clicker because we didn't get it to work. So
okay.
Here and I'll move your slides. You can be.
Okay. Well, thank you very much. Thank you for that introduction. And thanks for everybody here for having turned out. It's very nice to see you all. It's very nice to be back. Maybe some of you are intrigued by the title. What does computation have to do with philosophy? And to introduce that in an informal sort of way, next slide. You're not a very good clicker, are you? No.
It's working.
Right. Okay. A warning is that what I've done is I've broken a lot of the slides up into very short segments. So it'll be next. Remember occasions from my past where conversation over lunch has taken a philosophical turn. And the first quote I'd like to make is from my own friend and colleague, Mike Baines of the University of Reading in the UK, who said it seemed to him that computational fluid dynamics was studying the dynamics of a computational fluid. And there's a great deal of truth in that. And it's something I'd like you to bear in mind because that's how I'll be thinking of things. There's stuff going on inside your computer. You hope it behaves like a fluid. How do you make sure it does behave like a fluid? Next. And Saul Abarbanel from Tel Aviv, and a similar person has remarked that when he saw a mathematical technique being demonstrated in 2 dimensions, he always assumes that if the author did not say it was trivial, it must be impossible. I'll be showing you a lot of stuff in 2 dimensions. The extension is trivial. It all started in 3 dimensions. It's a method of descent to take it under 2 dimensions. Next. So from a more professional point of view, the Marxist philosopher Slavoj Zizek said the purpose of philosophy is to ask the right questions. And he went on to say that questions are actually more important than answers, because after all, what is the use of the right answers of the wrong question? Next, you're getting the hang of it. The educational philosopher, Matthew Lipman, said the right answer to the right question is a candle in the dark. And I really love that. He was thinking of teaching a new concept to a student to whom all is initially darkness. You find the right question, suddenly there's an area illuminated. And you don't turn on a light to illuminate the room. You follow a much more old-fashioned technique. You walk around the room, lighting candles one at a time. And the most important candles are the ones that show you where the next candle is. And Albert Einstein said that if I had an hour to solve a problem, and my life depended on it, I use my first 55 minutes determining the proper questions to ask. Now, I'm very much in his shoes because I have an hour to convey some ideas to you, and I'll spend the first 55 minutes asking questions. At the end of it, if I actually was Albert Einstein, I would have all the answers. But I'll have some doubt at least, and I hope we can there. Again. And so asking a lot of questions, and some of those questions I do know the answer. I also know how to interpret the answer. I know how to use the answer. Sometimes I know the answer, but not the meaning of the answer. In some cases, I just like to know the answer. Next. So, in philosophy, one asks different sorts of questions. One asks, for example, the question, how should I lead a good life? And you can buy lots of self-help books that will assist you in that. But you can also say, well, what does it mean to lead a good life? Is a good life one that leads to power and influence and wealth? Or is a good life one that leads to inner contentment and the ability to be of service to others? And you say, well, maybe can I have both? You need to answer that question first before you can say, how do I lead a good life? You need to know what a good life is. So I'll be concerned. I think, yeah. We ask a lot of questions in CFD. We say, what variables should I use? What sort of grid should I use? Where are variables placed on the grid? Do I use a semi-discrete method or a fully discrete method? Do I use a finite volume method or a finite element method? All of those questions rather presuppose that you know why you're asking the question. And so I want to try and dig a little bit deeper than that, if I can. But certainly one extremely good question is, what information should I use to advance the CFD method? I want to know what the solution is at this point, at this time. What is the information I need? And a very good answer is we must include all the data on which the exact solution depends. So put technically, the discrete domain of dependence should include the exact domain of dependence. This is the famous Courant rule. If you're teaching CFD, you teach this in the first class. Everybody says yes, 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 yes. But, and that isn't really a mathematical theorem, by the way. That's just common sense. I mean, how could it possibly be otherwise? So something else that is also just common sense is, well, you should not use any data on which the answer does not depend. I mean, that would be stupid, wouldn't it? But when we're solving hyperbolic problems, there are very clearly defined domains of dependence. There are data that is relevant, data that is not relevant. And so how big should the stencil really be? So this is a philosophical question. We should use only that data on which the exact solution does depend. This is almost impossible. And we can do it in some cases. For instance, in linear vector in one dimension, we know exactly where the data comes from. Most probably it's much more complicated than that. And continue. We usually know by analyzing the differential equation where the information should come from. But to actually get to it in a computation requires some form of interpolation. What the CFL condition really tells you is you must use data on which the solution does not depend. That's quite a revelation. It should make you think hard. So let's take the simplest example, just linear direction in one dimension. And the best way to solve this in a finite difference sense was worked out in 1981 by Isles and Strang. And they constructed a stencil looking like this. So the best way to do it is to have one more point in the upwind direction than in the downwind direction. And you should interpolate a polynomial in that data. I'm only, by the way, going to be talking about odd order methods, because one of the things that's fairly easy to establish is that for advective problems, odd order methods are better than even order methods. They have more balanced errors. So this will give us a fifth order method using 6 data points. And I've always told people when I've been teaching them, well, all you have to do is you have to interpolate to this point here. This is the only point that really matters. And I'm not really sure that is an interpolation problem. It looks like an interpolation problem. It would be an interpolation problem if this was nice, smooth data. But in hyperbolic problems, you very seldom do have nice, smooth data. You have discontinuities for all sorts of reasons. And then what you're doing is you're extrapolating from outside the domain of dependence into the domain of dependence. You're extrapolating from the other side as well. So this is not as simple a process I've often led people, tried to lead people to believe. So going back to the question of what are good questions, how do we ask good questions? Well, we begin by asking bad questions. We have no choice. Sometimes we even ask silly questions. I always tell students that asking a silly question is the first sign of progress. And then we progress from there. It's certainly better than not asking any questions at all. And it takes time to determine whether a question is a good question or a bad question. The determining factor is, what do we learn from the answer? We don't know to begin with what we will learn from the answer. And a good answer to a good question, as I said earlier, is a candle in the dark. It suggests the right places to look next. So a very famous question in the history of CFD is the question asked by Sergei Godunov. If I have a hyperbolic problem to solve, and I had to solve an initial value problem, and suppose the initial value problem consisted of piecewise constant data, how would that evolve? And it turns out you can answer that. So that's one of the criteria. This question does actually have an answer. You answer that by solving Riemann problems for the interfaces between the constant states. It acknowledges the nonlinearity of the problem, which is not easy to do otherwise. And it's been incredibly successful and influential. And most of the compressible flow codes today and codes for other sorts of hyperbolic problems outside of aerodynamics are so-called Godunov type methods that at least borrow from this idea. Whereas an incomplete question, it doesn't lead to very good results for incompressible flow, nearly incompressible flow. It's rather silly, in fact, to think that the flow around the smooth leading edge of an airfoil can be approximated by a set of Riemann problems. It looks nothing like that. It's amazing that it works at all. And it can be rescued. People have so-called all-mark schemes, which introduce imaginary physics to get around the difficulties. And these are much inferior to specialized incompressible flow codes, which give orders of magnitude better answers. It's a bit puzzling to know why that should be so, because it's just a special case. Also, it employs only one-dimensional physics, and one-dimensional physics is not representative of low-speed flow. And it also does not distinguish correctly between different types of information transfer. Is there a better question? So I'm going to ask a completely different sort of question. Why are we all here? This is looking forward to the talk that I'll be giving in Cambridge in March at the Cambridge Symposium on Compressible Flow. And we're all here because we're interested in compressible flow. We're all interested in partial differential equations. We're all interested in digital computers. What do these topics have in common? That would be why we're all here. And what they do have in common is they're dominated by the transfer of information. Inside a digital computer, there are storage units that communicate information to each other. Inside a fluid, there are fluid elements that influence other fluid elements. So we would like that information flow to be as close as possible in the two situations. This is the computational fluid that computational fluid dynamics is about. In elliptic problems, everything depends on everything else. But in hyperbolic problems, there are very specific channels of communication, which I think have to be observed. And indeed, the Courant condition says, yes, you must observe them. But it's a little bit loose in the way it specifies that. So I'm going to concentrate on the hyperbolic problems. And there are two principal types of information transfer. Mathematically, a lot of things are different things are possible, but very, very common indeed is that there is some kind of advective process where the fluid picks up information from somewhere and just carries it elsewhere to scalar quantity. And then there's something I'm going to call a pressure flux because that's what it is in the Euler equations. The other thing that's going on, some bits of the fluid are influenced by the pressure in the neighborhood of the fluid, but in MHD or solid mechanics, there are other things going wrong. We're going to call them all pressure fluxes. I mean, the stuff that goes through the fluid rather than with the fluid. And these processes are different, and they deserve to be treated differently. It really doesn't matter all that much in one dimension, because everything just travels either to the left or to the right. So there's really only two sorts of information process. It goes left or it goes right. In higher dimensions, there are much richer set of processes going on. So thank you. So nevertheless, I'll go back to the simplest one-dimensional problem. And this very simple equation teaches a lot of lessons that apply more generally. It's important to realize exactly what they tell us. It's also important to recognize what they do not tell us. And so sometimes this is used as a source of information, but it doesn't really work. So I'll be showing you a lot of these diagrams, and I better take a little bit of time to explain what they are. The classical way of analyzing this is the polynomial analysis. So we take that linear advection problem, we propose some initial data. This is the real part of a complex function that representing a sine wave. That should simply translate without losing any amplitude. So there is exact amplification factor. This is the complex number by which this gets multiplied when after the wave has propagated over one computational cell. And there's going to be an approximate amplification due to our numerical method. Now, the exact amplification is on the unit circle. And so the exact amplification should be on the unit circle, but of course it never is. But you learn a lot from looking at this so-called polar dispersion diagram. It always includes this point here. This point says that theta equals 0. The frequency is 0. This is a constant signal, and it is not dissipated. It is not amplified or dissipated. So the point 0, 1 should always be on the curve. Then it follows the unit circle for a while, and how closely it hugs to the unit curve is what we call accuracy. There's something I want to stress, that accuracy is a low frequency property. This is something we can analyze. We can do Fourier series and stuff. And we find the accuracy is some power of theta, some power of theta by which this diverges from the unit circle. So that's accuracy. How close is it to hug the unit circle? Then there's the point at which it breaks away from the unit circle. And this defines what you call bandwidth. This separates the frequencies that are accurately treated from the frequencies that are not accurately treated. If the locus ever goes outside the unit circle, then it's unstable. high frequencies, well, you can't expect it to be accurate any longer. What you can ask, it stays well inside the unit circle, so it is damped out and doesn't do any damage. So this is what I call the healthy dispersion diagram. And we're seeing some dispersion diagrams that are healthy and some that are not. So this is the most traditional and the simplest way of increasing accuracy. This was the one that was studied by Isleys and Strang. And it is still very widely used, and it's the basis of more modern methods, like essentially non-oscillatory schemes, ENO schemes, where you use wide stencils to get different answers and you combine them in some way. But by doing that, you're not going to do it any better than the ingredients you start with. Well, this is the simple classical first order upwinding. Uses this stencil, has this dispersion relationship. Very nice. Does absolutely everything it should do. Of course, it's not really very accurate, it's only first order. You enlarge the stencil, you go to third order. You enlarge the stencil again, you go to fifth order. And you can see you hug the unit circle more closely every time you increase the order. Actually, you also increase the bandwidth. And you see you also do the right thing at high frequencies. These are all nicely damped out. So you're apparently doing everything that's you wanted to do. But I do contend you can do a great deal better. And I'll be showing you how you can do a great deal better. The reason why you don't do all that much better is because you're using all this information, which is a long way away from where you really want to have it. So that's how to do it, number one, how not to do it, number one. Next. How not to do it, number two, is much more modern, much more fashionable. And it's called the discontinuous Galerkin method. And no, it was still, oh, sorry. Yeah, so this is really what all what I just said, sorry. Next. Discontinuous Galerkin method. You do start with this simple first order stencil. If you're going to increase the order of accuracy, obviously you've got to do more work. So you've got to do more work on something. And what the DG method does is it retains as local variables information about the derivatives or the moments of the solution. It does this all in a very compact way, but it is semi-discrete. It gives you ordinary differential equations, which you then have to march in time by a Runge-Kutta method or something. All the results I'll show are for Runge-Kutta 4 time stepping. These are almost universally used in practice. And when we see something, so if I take the current number at a half, it's actually unstable. We go outside the unit circle. Although to begin with, they're very good. We really hug that unit circle very nicely. Increase the current number to 0.464, and this locus has touched the unit circle again on its way out. So this is the boundary of stability. 0.4, everything is sort of okay. 0.3, even better. The point I want to make is that by doing the Runge-Kutta process, by doing the semi-discrete process, you are bringing in information which is not the information you want. You're bringing in information from outside the domain of dependence. And what happens when you do that is a bit unpredictable. Sometimes one thing happens, sometimes another thing happens. But what happens here is that we lose the rate of advance. We lose the CFL condition. Next. No, back. Sorry. Yeah. Yep. So a point I want to make is, well, you reduce the CFL condition to something like 0.4, say, which means you're taking only 40%, or one way of looking at it is you can only take you're going to need a cell size that is bigger by 1/4%. And so you need more resolution in the space direction. You also need bigger time steps. And in higher dimensions, that's going to multiply because you're going to need that extra resolution in all the directions. So for 3 dimensions, whatever improvement you get in one dimension, whatever improvement you get in the spatial resolution is raised to the 4th power by the time you're talking 3 dimensions. So these apparently small distinctions are much more important than they look. The other thing I want to mention is I've taken the frequency here up to a frequency of 2 pi rather than pi in the earlier case. And there's a well-known and possibly slightly wrong assumption. You always need 2 points per wavelength to resolve a signal. Let's take the next slide. Because of the so-called folding frequency, sometimes called the Shannon limit or the Nyquist limit, if you have 2 signals which one of them has a frequency slightly bigger than pi, the other one slightly less than pi, then there will be places at which they coincide, and you don't know which one you're processing. On the other hand, if you look in some areas of signal processing theory, which I'm not very familiar with, there's something called Papulis's theorem that says you can distinguish between signals up to a frequency of n times pi if at each sample you do not simply take a single measurement. You take n different measurements, you have more information. You can tell if you knew the derivatives, you could easily tell these signals apart. So Papulis's theorem says, in principle, it doesn't matter what extra information you have. You just need enough of it. Now, that's clearly not true in practice, but in theory, that is the result. This is another example of a question where I know the answer, but I'm not completely sure what the answer means. But anyway, this is called multi-channel sampling, and I'd very much appreciate it if there's somebody else in the audience who knew more about this than I do. So, accuracy is not the solution. Accuracy is dealing with this part of the diagram. And I like to make the analogy, this is like trying to deal with a poisonous snake by grabbing its tail. And the common belief is that if you grab its tail more firmly, you will control the head. I'm not sure I'm completely convinced by this. Accuracy, again, I'd say is an asymptotic property. The difficulties occur at the high frequencies. So I'm going to have something to say about that. High order accuracy, you believe, will extend from here all the way around here. Actually, it doesn't. Next. So what I'm going to be recommending very strongly is the use of the correct stencil to advance the solution through the correct information. I'm showing you results for a 3rd order scheme. I've already showed results for a 3rd order scheme. In this case, you'll see that the resolved frequencies are much larger by a factor of about 2.5. The degree of accuracy, the closeness of the approximation at low frequencies is also increased by a factor of about 2.5. Stability is increased by a factor of about 2.5 compared with DG. Cost, I put in inverted commas because I'm assuming everything costs the same, but I'm just talking about the number of times you have to do something. So the number of times you have to do something is reduced by a factor of 39 in 3 dimensions. All the high frequencies are very well behaved. But it's not really going to be 39 because this will be a bit more complicated. But 39 is a big number, and it will compensate for a lot of additional complications. So the scheme I'm talking about was really invented by Brahm in the first place. This is Brahm's scheme 5 from his 1977 paper. each cell owns 2 degrees of freedom. So the cost is only that of 2 degrees of freedom per cell, but it shares the degree of freedom with its neighbor. And so each of these shared degrees of freedom does double the work, and so you reduce your storage costs. With this edge value, and this average value, you can reconstruct a parabola. Inside that parabola, you can interpolate to find what is going to be leaving the cell on the left-hand side. So you find a new right-hand value at the next time step. You also integrate underneath this curve, and you find the amount of stuff that is leaving the left edge. And so from conservation, you find what the new mean value is. And so that's what the scheme is. I'll be concerned with some generalizations of this. This scheme has some beautiful properties. The one thing, and perhaps I shouldn't be saying this, because it could give you a continuous result, you don't have to solve any Riemann problems. Not that solving Riemann problems is a bad thing in one dimension, because Riemann problems in one dimension do reflect the real physics. But in the extension to higher dimensions, you don't want to be solving Riemann problems, because Riemann problems there do not reflect the proper physics. The procedure is valid right up to both boundaries. So there are no special conditions to be fulfilled either at inflow or at outflow. It's stable up to a current number of 1, which is as much as you can expect. It can be coded as, when you generalize it, it can be coded as a loop of elements. So you don't have to talk to your neighbor before deciding what to do. And that cuts down on communication overheads. Discovered by Brahm in 1977, subsequently rediscovered by lots of people, all of whom fell in love with it, but none of whom discovered how to make the proper extension to higher dimensions, including, I had to say, Brahm himself, who thought that it was a great idea but couldn't see how to, well, what he says is that people talked him out of it. They didn't want to get this complicated. It's not that complicated. And it does apparently work beyond the Nyquist limit. Those diagrams I show you, they hint as though they're going to go past pi. Don't really do it, but it's promising. So back again, yeah. So here is a comparison between that method, the active flux method, and the discontinuous Galerkin in the DG1 version. So far, just talking about linear advection. A packet of waves. If you look at the base of the wave, you can see that the active flux results are always much more resolved. They're actually pretty much in prediction with that theoretical prediction of F2.5. The overshoots are less, and they do not contaminate the regions in between the waves as much. So these are properties that I want to try and extend to higher dimensions and more complicated problems. So 2 dimensions, I've become a fan of unstructured grids. I find myself constantly amazed by what you can do with triangles. What you have to do with triangles is decide where you're going to place the information. And obvious places to put the information on the vertices. If you just use the vertices, you can define a linear reconstruction inside the triangle. This will give you a first order scheme. This is known as the lax element. If I put values at the midpoints of the edges as well, I get a Lagrange element with 6 degrees of freedom. I give you a second order reconstruction and a third order element. I can also add gradient information. So I add the gradients along the edges, the gradient from the midpoint toward the center. That gives me 15 degrees of freedom and a 4th order reconstruction, so a 5th order method. I'll be showing some results of that later on. And this does extend to 3 dimensions. My recent student, Iman Samani, did a study. There are many other choices, but it's a little bit obscure at the moment exactly how many choices you do have. But there are some very useful choices that are really not known to finite element theory. So progress in one dimension depends on identifying some useful model problems. The only model problem we really need in one dimension is linear advection. In higher dimensions, the analogy is not really as useful as you would hope. So although a lot of work has been done on this problem, it's not very good because your real problems don't look like this. They only look like that if they're what we call simultaneously diagonalizable, and very few problems actually are. A much better problem is to look at the acoustic system, in which changes of pressure are driven by the divergence of velocity, changes the velocity are driven by the gradient of the pressure. And I steered clear of this for a long time because it seemed to have so many unknowns. I wasn't sure how I would think about it. But actually, it's much more physically expressive than the scalar wave equation, although that's what I'll start with. But in fact, I need both models. I need something like this if the problem really does look like that. I also need this, and I need both of them in nonlinear versions. And between them, they'll solve almost all the types of continuum problem that's come up. An important property for solving hyperbolic conservation or disconservation, if mass should be conserved, then mass must be conserved. And a classical definition of this from the finite volume world going back to 1960, you have this one-dimensional conservation law to solve. You solve it in a finite volume form. You have some inter-volume fluxes, which depend on a lot of surrounding states. And if, when all those states are the same, you get back the correct solution, you have a conservative method. I really need a definition a bit more general, a bit more flexible than this. And so in multiple dimensions, I have some sort of volume around which, and this is just in 2 dimensions, it will be the same in 3, around which I can define a conservative residual. And it will have the property, because it depends on the boundary data, the integral along this side is the same for the neighboring cell, but of opposite sign. So these will cancel when I add everything up. So if I arrange it so that all these cell residuals add up to the boundary residual, I'll have a conservative method. I can add these changes anywhere in the grid, provided I add them somewhere. The result will be conservative. If I add them all inside the same cell, I get an additional property, because I won't need to communicate with my neighbors. I won't need to know who they are, where they are, what they are. I just keep on doing internal things inside each cell until the end, when everything gets added up together. So that's what's being done in all cases here. For the advective part of the problem, it's very instructive to look at what are called the pressureless Euler equations. So you simply write the Euler equations down, you say there's no pressure, there's no such thing as pressure. And this is actually useful for certain sorts of plasma modeling, modeling of interstellar dust, things like that. What this does is it models a set of particles that do not interact. Once you set them, they all go with the same speed forever and ever, until they collide, but I'm not concerned with that. And from this, you can deduce that the velocity satisfies this generalized Berger's equation. And the density comes from knowing the stream tube always contains the same mass. So they have, for a stream tube, rho times A is constant. This can be made the basis of a series solution. And all that was worked out by my student, Brad Bang. It's a bit too much of a side issue to go into here, but he wrote a nice thesis about it. For the acoustic part of the problem, this is where we get very classical. You go at 1807. And Poisson's solution to the initial value problem for the 3-dimensional wave equation. So we have a wave equation in 3 dimensions for some quantity phi, which depends on what is called the spherical mean. I have something phi, which is the function of three-dimensional space, and its spherical mean here is the average over the surface of a sphere drawn around it with some specified radius. Radius that I'm concerned with is the radius of the sphere of influence for the acoustic problem. So time times sound speed. And then the solution at this point at some new time is that solution at the 0 time plus the spherical mean of the time derivative around that sphere at another integral involving the second derivative around that time. This looks a bit like a Lax-Wendorf expansion. Lax-Wendorf expanded the new solution in terms of the old solution, the first derivative and the second derivative. What's rather special about this is that this formula includes all the derivatives. This integral here tells you about all the odd order derivatives. This integral here tells you about all the even order derivatives. So although this looks complicated, this is all you will ever need. And so that's the comment I make there. And so my student Tim Iman in 2013 worked out how to apply this not to the scalar wave equation, but to the system wave equation. The system wave equation is more interesting because it includes vorticity, and it's more physically expressive. And the form is the same. This is derived in 3 dimensions, but it applies in 2 dimensions because you just assume there's no dependence on the third direction. It also applies in 1 direction. You assume there's no variation in this direction or in that direction. In that case, what you get back, of course, is the method of characteristics. If it's exact in 3 dimensions, it must be exact in 1 dimension. So this is unlike most unwinding methods which start in 1 dimension and kind of claw their way upward. In fact, it goes upward above 2. So there are these results apply in any number of odd or even dimensions, which is intriguing. And the other thing is that these integrals are actually quite easy to compute. They don't look easy to compute. This is off-putting at first glance, but that's actually wrong, and I'll come back to that in a bit. So how do I solve a 2-dimensional acoustic problem? I set up a triangular grid, kind of do set up a triangular grid. Each triangle has degrees of freedom at these points. I want to take these integrals over a disk enclosing those points. Each triangle contains some segments of those disks, and I visit a triangle. I work out these integrals for all of these segments. Then I visit the next triangle, visit the integral for all of those segments. Then I finally come back and do a loop over the vertices and add up all the segments that pertain to it. Okay, thank you. Now this and that has some very nice properties. One thing is it preserves vorticity. The acoustic equations say the initial vorticity you start with, you should finish up with. And most numerical methods do not have that property. They create vorticity or they destroy it. In this case, the vorticity is preserved. It goes to the correct limit at low Mach number. So although this is derived by considering fully compressible flow, it applies all the way down to incompressible flow. It has a built-in radiation condition. So suppose this is an external boundary. People normally go to a great deal of trouble to write down the boundary conditions that apply to the nodes of the cells on the edge of the boundary. You don't need to do that. You say, well, there is no cell out here. There is no data out here. There are no incoming waves. That's what you want to say. It can be coded efficiently, and that was found by early this year. This is Doreen Phan's experiment. Very nice experiment. She computes a circular wave starting somewhere around here. It spreads out because the domain is a rectangle. The wave leaves at the sides, but does not leave at the top. Now, if you don't do anything at all, or you use conventional methods, you expect to see a reflected wave coming in from the sides. You do see it. There it is. But it's very small, and it is smaller than you would normally get by applying the best available non-reflecting boundary condition. She did a different experiment in which she did this on a large circular domain, and then, of course, the wave stays in that domain. It's no problem. And if you do on a small circular domain, if you do on a small circular domain, it reaches the edge and then there is maybe a spurious reflection comes back in. There is that spurious reflection. So this is, however expensive this turns out to be, here's a large countervailing economy to be taken into account. Yifan Bai looked at these 6 integrals that have to be evaluated inside the computer, and she found they were not all independent. And in fact, if we label the means 1, 2, 3 associated with the vertices and the means 4, 5, 6 associated with the edges, there is this matrix equation which connects them. So you only have to work out half of them. And of course, you begin by calculating the easy ones, which are the ones at the edge. And so you reduce the cost, again, quite considerably. So we do have a cost comparison. This is comparing with discontinuous Galerkin. This is a plot of the L2 error against the reciprocal of the mesh size. Slope here, very nice slope of 3 in both cases, indicating third-order accuracy. So I think both methods are coded correctly. Then we plot the accuracy against the CPU time, and there's almost an order of magnitude difference. So doing the right thing pays off, even though it costs you a lot. And I think that's going to be, I hope that's going to be a continuing justification for this line of work. She did tell me what answer was very interesting. So here is the kind of 3D wishy-washy hand-waving sketch of what's going on. Here is a cell at the initial time level. Here's the same cell later on. What you're doing is you're calculating what's going on inside these cones. And in particular, what you're doing is you're calculating what's going on along this axis. So like this, you have a history of the solution against time. And we can make available that history from a high-order method and from a first-order positive scheme. If we then borrow an idea from flux-corrected transport, we can combine these to produce a limited scheme which eliminates the oscillations. And we applied this to what is actually a very difficult problem, which is an imploding shock wave. So, yeah. We did do this with full order equations. What I'm actually showing here is results for this model system, so-called P system, in which the density is driven by the divergence of velocity. Velocity is driven by the gradients of an isentropic pressure, even though this isn't an isentropic flow. And the initial data is a region of, a circular region of low pressure inside a region of high pressure. So a shock wave moves inward. And here it is starting out. We show results without the limiter, with the limiter. Results with the limiter, and I think there are probably better limiters available. That's something I'm working on. But we see the shock wave moving inward and sort of develop a peak. This peak is genuine. Moves in closer, peak gets stronger. Moves in closer. In theory, that pressure would go infinite, and the analytical solutions for this, in which the pressure and the velocity reach a singularity at the origin, and the shock rebound and starts moving out again. We can see the rebound as well. But what I'd like to show you is the results just before, or just as the shock reaches its point of minimum radius. And it's looking, I'm slightly disappointed with the way this has come out, but what you can see is it's very circular, even though it collapsed into only being defined by about 3 of these unstructured elements. So it's very circular, and then it rebounds and goes out again. How close it can go in, I say it should be able to collapse right to the origin. In practice, how close it gets depends on the size of the mesh. It will collapse into within about 2 or 3 mesh widths, whatever the mesh size actually is, a higher pressure. So what all this has done is convinced me that local treatment and relevant treatment is of the utmost importance. And so how can you go beyond, that's given me 3rd order accuracy, how can I go beyond 3rd order accuracy and still say local? Because clearly I've got to process more information of some kind. So the only way to do that is have more information inside the cell, as the discontinuous Galerkin method currently does, but I want to use it in a better way. So I'm here stealing an idea, the Hermite spline, which, as I say, is universal in machine manufacturing, computer graphics, machine-aided design. You have data at 2 points, you know the positions of those points, and you know the direction of this curve. In higher order versions, you know more about those curves, you know their curvature and higher derivatives. But in all cases, what you can do is you can find a polynomial curve that joins those 2 pieces of data. But it's almost unknown in CFD. There are few papers, but very few. So going back to 1 dimension, there's something called Hermite interpolation. The data at each grid point consists of the value of that grid point, and it's a vector which has that as its first entries. Higher entries are the various derivatives at that point. And there is a function then that joins those 2 grid points. As again, it's a vector between the grid points. It is some matrix times the data on the left-hand end of the interval, and some other matrix times the data at the right-hand entry. A and B are constant matrices. To use that for linear advection, we say the new value is a combination of the 2 old values, depending on where the interpolation point lies. And this had odd order actually, which is again a nice thing, the order 2p + 1. These turn out to be always stable for a current number less than 1. Bringing Brownback in again, the phase error is 0 when the current number is 1/2. And the same symmetry property carries through to this situation. And it's conservative, even though it didn't look conservative, it's just interpolation. But it just so happens the errors cancel, and it is a conservative method. This is very new, and I don't know nearly as much about it as I would like, but I am excited about it. These are the dispersion poles. The 3rd order scheme, we see improved error, we see improved bandwidth. We see that the high frequencies are well behaved. We go to 5th order, we see again, very much improved low frequency behavior. 7th order, we see accuracy extending well past the Shannon limit, the Nyquist limit. This one is a bit of a mess. I think I might have given Maple more than he could chew. I have to clean that up a bit. There's early days yet. Here's an attempt to do this in 3 dimensions, in 2 dimensions rather. So we have a quartic element which contains these derivative degrees of freedom. This does not appear anywhere, as far as I can tell, in the finite element literature. And we're solving the elastic wave equation, so we're solving something a bit more complicated than acoustics. In solid elastic dynamics, there are two sorts of wave. There are so-called P waves, which are compression waves doing this, and the S waves, which are torsion waves doing that. And it was a discovery of my student Shuichi Nakazawa in 2001 that you can write these as two independent first-order systems. They have identical, but they have different wave speeds and different behavior. One depends on the kernel and one depends on the inversions. Okay, I'm very close. So the problem is this: we have an unbounded medium which is divided in two, and we have one set of properties on one side, one set of properties on the other side. Simultaneously, we launch two small explosions that create both sorts of wave. And inside each square, there is an unstructured group which is only 30 by 30. So by today's standards, this is a very coarse mesh. Okay, thank you. And I'm not going to spend a lot of time talking about the results because, first of all, I don't have very much time. Secondly, I don't understand them. But pretty much everything we expect to see here is, in fact, here. And it's very nicely and crisply resolved. One thing I want to point out is that here we have a transient wave that is confined to the interface. And that's something that should happen. It hasn't been built here, but it does happen. We have waves that leave the domain without being reflected. So that works as it has done previously. And here we have things evolving to a later time. I'm just saying this is good news. And yeah, can you make one more? Yeah, one more again. And there's no cross-talking between essays. So taking it further yet, when we go to the Navier-Stokes equations, we can write the Navier-Stokes equations in a hyperbolic form by including the derivatives as unknowns. And so we can use all the tricks that we learn about for hyperbolic problems. We can use those on the Navier-Stokes equations. Here is a Navier-Stokes calculation. It's the first of its kind. It is compressible. It's only at a very modest Reynolds number, but it still indicates it all works. And I think that's where I'm going to leave it. And I'm going to thank you all for listening. Thank you.
Oh, what an amazing talk. Just like you think you have 55 slides, but you have 131.
Yeah, well, that's because all the subsides.
Exceeded my expectations by it. It was an amazing talk. I mean, and we have a faculty opening. I don't know.
Oh.
Anyway, so yeah, I'll open it up for questions. Go ahead.
Yeah.
You show lots of really nice properties of these schemes.
Yeah.
What do you see? What do you see as the limitations of these schemes?
Right. One thing I see, for instance, are things like sonic boom. I think this is a natural for sonic boom. I am in contact with the guy at JAXA who is very interested in this. Another natural application is large edge simulation, where there is a gap usually between the resolved scales and the model scales. I think I can narrow that gap, and I'm sure something good should come of that. There are generally multidimensional problems. The dimensions higher than 3. And so the Vlasov equations, for instance, even looking into the row distance, the Einstein equations for special and general relativity. I've started to believe in high-order methods. I used to be against high-order methods because I thought they were always going to be too expensive, and the accuracy was going to be a delusion. I think the accuracy can now be genuine. But more generally, the ability to use coarse grids means that, I mean, this is not something that attracts people immediately. Oh, I go away, put that in my code and try it out. No, you're writing new code. I'm sorry. But I think it will be worth doing that. And time will tell how many people do it. From.
Phil, you mentioned Navier scope. Does it have any relation to what Hiroaki Nishikawa is doing?
Yes. And we're using his decomposition.
I have a question. So it was amazing to see that you were showing at least an order of magnitude improvement over DG.
Yeah.
How much of it is simply because of the fact that you have a fully discrete method and they have semi-discrete? And how much of it is because of all the other things you did?
That's a really good question. It's very hard at this stage to disentangle everything. But I've really think that semi-discrete methods violate everything I believe in. And so I'm against them.
I agree. So, yeah. The questions? So I have one, maybe I want to go back here. So I've never seen these kind of plots. And this was what I was complaining your students' thesis did not have, but you have them.
Yeah.
So, any particular, sorry. Oh, it's not visible.
Yeah, these plots do need to be read with a bit of caution. I didn't give a complete explanation. I gave a quick bluffer's guide because I thought that was all I had time for.
Yeah, because I've never seen things like going towards the damping limit like here.
Yeah.
I've never seen a single method that have that property. So I don't know if it's a particular quirk of that CFL number or.
Well, those things happen because you're solving fairly high order polynomials with complex coefficients. And Maple seems able to handle this, but with difficulty. And I have to coke these diagrams out of it. I'm not completely sure what I'm doing. But I think these are genuine.
Thank you. Ram.
Yeah, about the Hermite polynomial. So, did I understand correctly that using the Hermite polynomials, all the information at the place where you also compute the active flux, they have an advantage over the DG.
Yes, I mean they both work by carrying more information in the same place, but they do it in a fully discrete way.
Yeah, I would not have expected that Hermite polynomials would do better.
Yeah, and some things I haven't shown is they also do extremely well on a square wave. Their traditional merit is for elliptic problems where you want smoothness. Conventional wisdom, Amagodinov, is you don't want smoothness in your reconstruction. In fact, there's nothing wrong with smoothness.
I do think that the reason they work so well is that you have all the information at the place where you need the active fluxes. Is that correct?
I think very firmly that is correct. And so the question I would ask today, if we're in with the new set of equations, is how local can I make them? How local can I make them? And you know, we discussed a long time ago making everything hyperbolic. And I think it's a good step in the right direction.
So I have a slightly different process question. So you started on moving in the active flux direction when?
Ooh, 2006.
and almost exclusively you've been working on these problems.
Yeah.
Over the past 17 years or so. And it almost feels like your comment about, taking a candle in a dark room and moving around, that is what has happened, because there is no way you would have foreseen all of these things.
Right.
And
Right.
you even mentioned when we met earlier, this is a lesson for everybody, that you learned something about linear advection, that it's not an interpolation problem.
Yes.
60 years old.
Yeah, after teaching this with great conviction, I was wrong.
That was amazing to hear. In any case, any last question? You have one?
Yeah, so one of the problems for that we face in Johnny Num's particular is grid dependence. So
Yeah.
how strongly do you see grid dependence with your active form?
Goes away. I can show you many examples where, well, on any grid, it goes away. But there are cases where we've done the same calculation on a structured grid just divided into triangles, and a grid of the same density that is completely unstructured. And a completely unstructured grid usually does a little bit better because it's not biased in any particular direction. And when you introduce the one-dimensional physics, then, as you say, you give the grid far too much say in what's going on.
Would you say that for unstructured grids it acts better because you're distributing error more randomly because of more of an intrinsic property of the scheme?
I think it's more an intrinsic property of the scheme. You're not solving Riemann problems, even though people have very kindly named a Riemann solver after me. It's something I'm secretly ashamed of. Yeah.
So when you write an introductory book on CFD,
Yeah.
would you start telling the students right away that advection, numerical advection, is not an interpolation problem? Or would you leave that for the last chapter? Well, actually, not.
Well, that's an I'm actually thinking about. Yeah, I'm thinking about that. I would certainly tell them it looks like an interpolation problem, and they can just pick up an interpolation technique and it will work, but there's a reason to suspect it.
Polar dispersion diagrams before. Hopefully this is not a dark question. I'm just curious, you talked a lot about these compact stencils that can help get you to where you want to go.
Yeah.
And you talked about that right after you mentioned these 2-point stencils. So I'm curious if that's a connection, like the living or are they not related?
Well, in any number of dimensions D, the smallest cell you can possibly have has a number of elements D plus 1. So a simplex stencil would be, or a simplex element. And simplex elements have a lot of very nice mathematical properties. They also have the nice physical property that if you can get all your information packed inside that element, and if you know where it should be inside that element. So there is, for example, something called the residual distribution scheme, which is a kind of precursor of this, where you have some kind of element and you have as small as possible. You evaluate the time derivative and you decide which of those elements to update, which of its nodes to update. So the process of defining the residual is a central process, a symmetric process. The process of deciding which degree of freedom to update is something that reflects the direction of travel. Is that getting close to your question? If I have a 2-point stencil, I do this so one way of interpreting the Godunov scheme is the values are at points instead of inside cells. I have a left point and a right point. I solve that Riemann problem. I see that some waves are traveling to the left. I use those to update the left element. Some waves are traveling to the right. I use that to update the right element. Sometimes with the rarefaction, waves are traveling in both directions and they update both elements. Which is the entropy fix.
Okay. There's no last question, I'll ask one. I think his question, oh, watch out.
Yeah.
Close. I think his question maybe made me think like in a slightly different direction. So can it be considered as a effective way of doing multidimensional upgrading? Because I mean, one of the reasons the imprinting wasn't happening is because you're doing a truly multidimensional upgrading rather than a
Yes.
1D.
Yeah.
So if you take the linear advection and you did the corner transport method or
Yeah.
Lebesgue's truly multidimensional method, then would you see similar answers?
There have been a number of elements. There's a lot of stuff out there that calls itself multidimensional, which is not multidimensional. It's
almost all of them.
Well, no, I would say some of
I
them
will
are.
not ask.
Okay.
All right.
Okay.
Anyway, I think this was really an amazing thought, but also to see the process of you starting almost a decade and a half ago and you know, moving through it and addressing so many challenges here and getting something that's really useful. So thank you so much for your talk.
Thank you very much.
And all the best for your Cambridge trip as well.
Thank you.